So I'll be going to give you a presentation titled From Clean Room to Machine Room, which is about the Endeavor BrainScaleS-1, which you have heard about in the talk of Johannes. So let me still refresh your knowledge on what we call physical modeling of analog neuron circuits, which is at the heart of all the BrainScaleS neuromorphic systems we are building in Heidelberg. And this is the idea that every neuron and every synapse has a counterpart on the neuromorphic system, a physical model. And here in the top, you see a layout drawing of two neurons, very small, micrometer size, and they implement the adaptive exponential integrate and fire model. So the thing with the physical models is that everything you want the neuron to do must have some kind of circuitry. So there is dedicated circuits in every neuron for all the things that an ADX neuron needs. So resting potential, reset potential, threshold potential, and so on and so forth. So the question now is, why is this analog approach useful? And this is due to the fact that you get accelerated dynamics compared to biological real time. And you can think of that very easily when you just have a circuit of a capacitor and a resistor. And then you think of silicon chips. There will be very small capacitances and very low resistances. And the product of that is the time constant. So when you build these kind of neurons, you end up with an acceleration factor of about 10,000. That means that 1 microsecond on the hardware it can be thought of as a biological time constant of 10 milliseconds. And of course, also every synapse has to is represented by a dedicated circuit and has to match that speed up. So now we have one neuron, but of course we need more. And especially we need also many synapses. So here you see a photograph of the BrainScaleS-1 ASIC. This is about 5 millimeters times 10 millimeters. And you see the large block of synapses in part for the neurons and also other circuitry for the digital communication. Because these neurons communicate with spikes, and spikes are best transported digitally. So we have a mixed signal system. There's also a parameter storage of floating gates that control the individual parameters of all the neurons. So already one of these ASICs is capable of emulating a small neural network. But 512 neurons is not enough. We need more. And for this, wafer-scale integration is used. So you take a wafer of Heiken chips, about 400, and you add an additional redistribution layer so that you connect where you typically do not have connections at the reticle borders. And by this, you have one wafer which can be configured to emulate one neural net, everything running in parallel, everything running with the same speed up. But again, a wafer alone is not enough. You need something to house the wafer, to distribute power and to distribute input and output. And this 20 centimeter wafer is then put in a so-called BrainScaleS wafer module, where it is attached to a 14-layer MainPCB, and communication is done via 48 FPGAs, and they are connected via Ethernet. So the bandwidth to one wafer module is then 48 gigabits, and all the wafers, all the FPGAs are connected to one switch. You also need some auxiliary boards at the moment, for example, for analog readout. But this module is already pretty self-contained. For example, you only need one 48 volts external power supply, and everything else is already generated by power boards on the module. So now I give you a short tour of what are the steps that need to be done to put together a wafer module and to put it into operation. So the first test is that we take the wafer and do an optical inspection on a so-called wafer prober. You see this machine in the lower left, where you have the wafer on a metal thingy that you can move with precision, and then do an optical inspection. For example, you can see in the upper right imperfections, for example, from the post-processing. And this is important to do because at the later stage, you need to know where does the error come from. Is it because of an already faulty connection on the wafer, or is it something that comes from the assembly process? What we can also do here is that we attach a so-called needle card to the chips and then do individual tests of the functionality of the chips. And this is then using the same software suite as the full system, but only attaching individual chips. When the wafer is found to be good enough to be put into a system, you need to put it in together with a main PCB, so kind of a marriage, like in car manufacturing when you put the motor in the chassis. And for this, you need quite a good alignment between the wafer and the main PCB. There are structures on the wafer that guide the optical process, because you need to connect the PCB via these elastomeric connectors, fine pitch elastomeric connectors with the wafer. And in the upper right, you see an alignment jig where you then use a microscope to align the wafer and the main PCB optically, and then you do electrical tests. So in the lower right, you see boards that are put in the slots where later the FPGAs will be put in, so that you can measure all the resistances, and when good contact is made, or when it's not made, you iterate with this procedure until you are satisfied with the connectivity of wafer and main PCB. So then, of course, you put in all the other components that I've showed you, and then you can put it in the machine room. Yeah, so here you see a picture of the fully equipped machine room that we have in Heidelberg, and where we would give you a tour if the conference would be on site. You see all the cables that go to the switches, and in the center you see a cluster of commodity computers. So then we have the machine room, and as every machine room, you need monitoring of that. Yeah, so the machine room itself and the modules are tightly monitored. So there are alone 1,200 time series data per wafer module, and the granularity with which the data is taken depends on the importance. For example, temperature sensors are read out every few seconds, and then there is, for example, an alarm triggered or even an auto shut off, and the alarms and alerts are then generated and reported via mail and chat. There are also events generated, for example, for powering on and off the system or the individual FPGAs, so that we know at every point in time what is the system, in which state is it, and what has been done in the past. So if you notice something is odd, then you can look in the logs here and see, okay, maybe this FPGA was deliberately powered off, or it was powered off because of an overheating. As Johannes told you, you need some kind of calibration, and for the full wafer there are alone 111 calibration steps where you tune your analog storage to a certain parameter, and then you measure via the ADCs the response of the neurons, and then you get some calibration curves, for example, just some linear fits, and this takes about a day per wafer module, and does not have to repeat it often. Yeah, most of the time it's enough when you do it once, when the environmental conditions do not change. For example, when temperature stays the same, then you do not need to repeat that. So although we did this very fine granular testing, you also do tests when the system is fully assembled. So for example, communication link tests, because it always may be that a connection is not as good as you want it to be, and then you need to flag that. And we also do digital memory tests. So we test all the bits. And this is about 42 megabit per wafer. And then we all put that in an availability management database so that we can individually flag certain chips or subcomponents to have a map of which components can be used for a network. So we had from clean room to machine room. Now we have from network to hardware. And for this, we developed the BrainScaleS operating system, which has a typical onion structure. You have the hardware in the middle, communication, and then all the other layers surrounding this with the experiments at the very end. And we used the domain-specific language Pine to formulate the networks. And then there is software running which maps these networks, takes into account the availability information, maps and routes, runs, and then extracts back the recording of spikes and networks. So I see I'm over time. I'm sorry, I'll try to speak.
Yeah, it's okay to continue because there are no questions in the chat room. So you have another 2 or 3 minutes.
So if you want to know more about the software part, there we have a talk where Eric will describe everything in detail on Friday. So what we have done, or what kind of experiments we have done, for example, the Bayesian sampling, time to first spike coding, and also rate-based models of a deep network. And not only the published results are interesting, but we have over 30 PhD and undergraduate theses, for example, also on constraint satisfaction problem solving that you can read in the URL I've put below. So to somehow prove that the wafer-scale network works, we have a functional feed-forward chain put across all the over all the wafer, and you see here parts that are blacklisted in red. The stimulus is put in the orange parts, and the rest of the colorful lines are the routes that are taken. And for this experiment, 230 of the about 400 chips were used, with about 20,000 logical neurons that were composed of about 80,000 neuron circuits and 1.24 million synapses. Our next goal is towards a wafer-scale, full-scale, wafer-scale cortical circuit model. And so this became a kind of benchmark task that Markus Diesmann will also talk about in a later contribution. And the full model consists of about 80,000 neurons. This will not fit on the wafer because of the fan-in. We will downscale it to about 10%. And we did some mapping studies with realistic availability information. And we also need to do a bit of a conversion because that model uses current-based synapses, and on the chip we have conductance-based synapses. We also need to reduce the external drive a bit. And we also did simulation studies of the influence of parameter variations. And you can see in the lower right a comparison of the adapted and the original rates. They are not identical, but they show the general features that you see in the populations of this cortical model. And then that could be trained again in the loop fashion to maybe improve on the agreement. So what have we achieved for BrainScaleS-1? It demonstrates from clean room to machine room and from network to hardware of accelerated mixed signal wafer-scale neuromorphic computing. We have, of course, more in the pipeline. For example, we want to make the module fully self-contained. So there is already an on-module analog digitization that you can see in the upper right module. We are working on a horizontal configuration that's complying with the OpenRAC standard. And most interesting is maybe we have a next generation interim solution until BrainScaleS-2 wafer scale is done, namely that we replace the wafer with a PCB where we have individual ASICs of the BrainScaleS-2 generation. So then it is not about 400 chips, but more like 40 chips, because you lose the advantage of wafer scale integration. But we can reuse all the infrastructure that we've developed with a module, the FPGA, the monitoring, and so on. Also, we're working on interconnection via XTOL, which is a network technology, and there's a poster by Tobias that you can have a look. Thank you.